We're going to start with this lesson in terms of O levels. In O levels, we have already done what a magnetic field is. We already understand the magnetic field between the north and the south pole looks like this. We understand what a bar magnet and a bar magnetic field is actually going to look like. This is somewhat like this, exactly like the O levels that we've already done. And the magnetic field lines are pointing outwards and pointing inwards and south. Over here, they're going to look like this. So these are the things that we already know. So in this chapter, basically, we're going to try to understand what is this formula ILB sine theta, what it means, and how to solve questions regarding it, how the examiner is going to try to trick you with one of the common questions. And we understand how to represent the magnetic field lines with these arrows and lines around a conductor. So first, we need to accept, again, basic as O levels, that if there is a conductor, a piece of wire, let's say, and there is a current flowing through it, either this will be called as into the page, because if you're standing from this perspective, this is what the current is going to look like. And how does that actually make? So it could be connected to a battery with a negative terminal, right? In this way around, this is positive, this is negative. So the current is actually leaving the positive terminal of the battery and going into the page like this. Similar case over here, the current is coming out of the page. Standing at this point, this will be called as out of the page. So these are the three-dimensional representations. In 2 dimensions, this is represented as this way. So if the current was going into the page, that would be represented as a cross. If it was coming out, that would be represented as a dot. Now, this dot and cross is not only used for current, it is also used for magnetic fields. For example, if we have a magnetic field in this region that is actually going into the page like this, right? So this magnetic field can be represented as a series of cross like this in a 2D plane at least. Similar case for out of the page as well. So these are O-level basics that we've already understood, that we already know. Please make yourself familiar with the Fleming's left-hand rule, because that will be used in these questions in this chapter. We understand there is a force acting on a current-carrying conductor in the magnetic field. This is precisely what Fleming's left-hand rule is about. So what it is trying to tell you is that if, let's say, we have a north pole, and these topics are taken from DC motor and AC generator. So if this is a north pole, and this is, let's say, a south pole in terms of 3-dimensional understanding, and there is a piece of wire that is placed between them like this. And if this wire is carrying current, for the sake of example, either in this direction or in this direction, we should be able to apply the Fleming's left-hand rule to figure out the direction of the force experienced by the conductor. So if you wanted to draw, okay, so let's take this one example. Let's say the current is flowing in this direction. Okay, so if you were standing at this point, this current would look like, to your perspective, it would look like current going into the page. So if we were to draw this same idea in terms of 2 dimensions, this is what it's going to look like. North on one side, south on one side, and the conductor in the middle with a cross sign. So applying the right hand grip rule, notice that I'm using 2 rules at the same time. So right hand grip rule, if we use that, then we understand that the thumb points the direction of current. The thumb will be pointing inwards to the screen, and the curl of the fingers is going to go like this. You can pause the video and go first memorize, or at least understand Fleming's left-hand rule and the right-hand grip rule. This is not by Fleming's. So in this case, we understand the magnetic field is towards the right side. Over here, the magnetic field in the same direction, so the magnetic field is strong. Over here, they're in the opposite direction, so the magnetic field is weak. So the force is exerted from strong region towards weak region. So this conductor will experience a force downwards. Now, you could have found this by using Fleming's left-hand rule as well. What you could have done is point your first finger towards the right side, which is going to show you the direction of magnetic field, which is from north to south. This is your first finger, right? And then you could have rotated your wrist and pointed the second finger into the page like this. So this is your second finger going into the page. Again, maintaining an angle of 90 degrees. And if you do that, your thumb will automatically open up at this location. This is going to be your thumb. I've added the links of my O-levels videos that actually explain these laws and these rules in detail. You can go check them out. Otherwise, this is assumed that an A-level student already knows these basics before continuing in this chapter. So we've done point number 1. We are going to look at point number 2. In point number 2, there is actually a system and a machine that helped us to figure out the direction, or at least the magnetic field strength itself. The problem and the idea is something like this. So what we have done, we have made a setup that looks like this. You can ignore the things that I've written on the screen right now. We only are interested in the setup. So what we've done, we run a line carrying current in the magnetic field, and this is the magnetic field from north to south. We already know it is going to go like this. Now, what we want to find out, what are we looking for? You see, we are looking for this magnetic flux density. What are we looking for? We're looking for magnetic field density. How dense are the number of lines? You see, this is the only quantity that is not measurable at this point. Otherwise, the rest of the quantities can be measured easily. So what is the formula? The formula comes out as F equals to ILB sine theta. It is important to understand that sine theta, the angle itself, is actually between the current and the magnetic field. So if we write this down appropriately or correctly, that would actually go something like this. I cross B with sine theta. You see, when you go to higher physics, you need to identify whether this angle is between B and I, or is it with L. So we need to specify that this theta is with magnetic field and the current. Luckily, in our case, the current and the length actually are in the same direction, so it doesn't really matter in this case. So what we are trying to find out, we're trying to find out the magnetic field density, which is represented by B. We want to count the number of lines. We want to measure these number of magnetic field lines by this method. So what we do, we place this wire in the presence of magnets. When we pass a current through them, through a DC supply, we understand that a current carrying wire between magnets like this is going to experience a force. In our case, it was experiencing a force downwards. In this case, let's assume that the direction of current is such that the magnetic force that it experiences is going to be upwards. Let's say, for the sake of example, okay, if the wire is moving upwards, then it is actually pushing down on the magnet, which is placed on a beam balance. So what happens? The beam balance reading actually increases because the magnets are now pushing down, or they're experiencing a downward force because the wire wants to go out. So according to Newton's third law, if the wire wants to go out, it will exert an equal and opposite reaction in the downward direction on the magnets or the magnetic field, consequently putting down force on the beam balance, or at least the electronic balance, increasing the mass of the system, or the reading at least. So from here, we actually pick out the force exerted on the system. What do we equate this to? This is going to become the weight. So mg is equal to ILB sine theta. Now we are assuming that they are at actually 90 degrees to each other, the magnetic field and the current. So sine 90 is actually 1. So this equation actually narrows down to ILB sine theta becomes 1. We want to find out the value of B because this is what we don't know. So we make B the subject of the formula and we get mg divided by IL. You see, mg can be found by the beam balance, length can be measured with the meter rule, and I is found by looking at the value of the current. So there is only B left, which is the strength of magnetic field of this magnet that we were discussing. So this is the final understanding of, you can say F equals to ILB. A current carrying conductor in the presence of a magnetic field experiences a magnetic force. We don't know that. We can find it by using this formula. Okay, so another trick question that the examiner sometimes may ask from you is force per unit length. Find the force per unit length. Now, the students get confused by this, force per unit length. No need to get confused by this. What is the change in the formula? So if I write down ILB sine theta, I'm ignoring sine theta for now because we know that at maximum strength, we need sine to be 90, right? So if I'm asking force per unit length, please notice that if you bring length over here, the variable actually goes in the denominator and the equation comes out as IB. This is newtons divided by meters, which is force per unit length. So if such a question arises, please don't hesitate shuffling the variables to make the equation look like something that is familiar to you. So according to the syllabus, we have already covered these points, right? We have covered the system that actually helps us to measure the magnetic flux density, which is the value of B. Let's move towards the questions. I'm going to discuss about this magnetic flux density even more in the chapter of electromagnetic induction, so don't worry about this. For now, just hold on to this idea that B, since this is magnetic field density, actually wants to measure the number of lines the number of lines per unit area. So if the number of lines are higher, the magnetic field is stronger. If the number of lines are low, the magnetic fields are weak. And these number of lines are in physics referred to sometimes as flux. A fancier word for the number of lines, but this is what it means. So don't try to think about this in a complicated way. It's a very simple thing. So moving on to the question where we're going to use the F equals to ILB sine theta concept. So he tells you that there is a magnetic field of this value and there is a wire XY which is tilted at an angle of 34, and we know that the wire should have been at an angle of 90 degrees for maximum force, but right now it is not. So it doesn't matter, we're going to use the formula of F equals to ILB sine theta. So he tells us find out the force on the wire if the current is 5.4, angle is 34, length is 4.7. So everything is given. Let's apply the formula F equals to ILB sine theta. Now I'm sure that even at this stage, students do not convert the centimeter to meters, and that's totally on you. If you get wrong answers, it's your choice. It's your doing, not the examiner's. It's understood that the length will be in standard form and everything is going to be in standard format. So current is 5.4. I'm going to write down 5.4. Then the length is given as 4.7. So 4.7 using prefixes. Centi has been converted by using a power of -2. Then we have the magnetic flux density, which is 2.6 minus 3, 2.6 into 10 raised to the power -3 multiplied by sine theta, which is the angle between them, which is 34. So sine 34. When you put in these answers, you're going to get an answer of 3.69 into 10 raised to the power -4 newtons. Since our answers are in two significant figures, I will write down 3.7 minus 4. This question is interesting. This is going to be a repeated question again and again. For these parts, it involves the lecture of AC electricity. Please do watch that video to understand what's going to happen in this question. The first step is necessary and it is going to be picked from that chapter. He says that the RMS value, this RMS value is actually from the AC electricity chapter. So RMS value is 1.7. He says find the total variation. This is a common question. Please be advised, this is going to be repeated again and again. So first, if this is the RMS value, let's find out the peak value. So the peak value of the current is going to be found by multiplying the RMS value with under root 2. So we find out that this is going to be 1.7 multiplied by under root 2. The peak value of the current comes out as 2.4 amperes. What does that mean? It means that the current is actually changing in the wire because it's an alternating current. It is changing in such a way that at certain time the peak value of the current is 2.4 and at certain times it is going to be negative 2.4. Okay, so this is the variation of the current itself. Now we notice that the direction of current has to do with the direction of force as well. So when the current is, let's say, positive, for the sake of example, let's assume that the force experienced by the wire is upwards. And when the current actually changes, the Fleming left-hand rule is going to be applied in the opposite direction. So the direction of force will also get reversed in this way. So when he says to find the total variation, whatever force I'm going to find using this one value of current, I will multiply this by 2 because I can get the same answer in the opposite way. So the exact total variation is actually going to be from this point to this point, which is simply multiplying the answer of force with 2. This is a simple confusion that students generally find. So let's find out the F equals to ILB sine theta. We know that sine theta is going to become 1 because we're considering maximum force. This is going to be sine 34. Please treat this as such. This is going to be sine 34. So let's find out the current. Now the current is going to be 2.4 because we are finding the maximum force that is possible. And we know that RMS value is actually the average value, average force. So length is again, will be taken as centimeters. So this will be 4.7 into 10 raised to the power -2. B is given to us as 2.6 power -3. So really, we are just solving this question again with a different value. And then we have sine 34. But I'm going to do this directly, okay, as you should too. This will be multiplied by 2 because I've explained that why this variation is going to be in 2 directions. So I get my final answer as 3.8 into 10 raised to the power -4 newtons. What you can do is calculate this one individually for the sake of concept and then multiply this with 2. You will get the same answer, 3.8 power -4. So this will be 3.8 into 10 raised to the power -4. I hope that we understand this question. Okay, you can find this question with the relative marking scheme, and you can find what you are doing wrong probably. Again, this is the question that we actually started with. This is the same setup is actually given in the question to you. This also has a common question. I will discuss Tesla in the next question, the next part of this course. But let's move on to this question. So a metal wire, balance span, and there is a length of 6.4. Now he says that the length of metal wire normal to the magnetic field. What does that mean? That from this point to this point, whatever cross-sectional area is of this wire, it is experiencing magnetic field. So this is actually 6.4. So as wide as this magnetic field will be, is the length of wire which is exposed inside the magnetic field. The rest of the wire has nothing to do with the magnetic field. That's why this is going to be given to you. Even if it's not, then the rest of the values will be given to you. So the average current is, let's say, 5.6 amperes and causes a change of mass of 2.4 grams. He says, explain the direction of force on the wire due to the current. You see, he says that the mass increases by 2.4, which means that the wire must have exerted a force downwards, pushing it downwards. And as a result of that, due to Newton's third law, it actually came outwards, or it will come outwards. So what we were going to write down, that according to Newton's third law, if mass has increased, force by wire is downwards, but force experienced by wire is upwards. So the force on the wire is actually, or the motion of wire is going to be upwards. Okay, all right. So, and this Newton's third law idea is going to be very common in this type of questions. Calculate the magnitude of magnetic flux density. So we are supposed to find out the value of B between the poles of the magnet. Very simple to do. We are going to use the formula F equals to ILB. So we are left with F equals to ILB sine theta. And if we are assuming perpendicular magnetic field, this sine theta will become, with 90 degrees, it will become 1. So now be clever about this. We know that the force is being given to us in terms of grams. So we have to convert this force into weight. And the weight has to be converted in the form of mg, which is equal to current, which is 5.6, multiplied by the length that is given to us is 6.4. So 6.4 into 10 raised to the power minus 2. For God's sake, please convert lengths into meters. Okay. Divided by, and then multiply with B. So everything is going to get on the other side and get divided by mg, right? So mass is 2.4 grams. So I have to convert this into kg. And then G is 9.81. Divide this with this number, which is 5.6. into 6.4 into 10 raised to the power minus 2. Please put brackets on it using calculator, and you will get your answer for B, or the magnetic flux density, as 66 millitesla, or as the marking scheme has completely written this down like this. So this will be 0.066. Okay, then he says that a low frequency RMS value of 5.6 is introduced. He says describe quantitatively. Now, whenever he says describe quantitatively, then you'll have to solve the question and then discuss its values. If it had said qualitatively, then we could have discussed this theoretically only and we'd be done with it. But now we have to discuss it with values. Now, if this is the RMS value, then multiply this with under root to get the peak value, which is going to be I peak, which comes out as 7.9 amperes. You'll have to solve the question again using F equals to ILB to find out the value of mass. So now make mass the subject of the formula, and since we are looking at the variation again, it will again be multiplied by 2, because I had told you that if we are dealing with an alternating current, sometimes the current is positive, sometimes the current is negative. So sometimes the force will be positive, sometimes it will be negative. So the total variation goes from positive to negative. So that's why the end answer will be multiplied by 2. Anyways, let's find out the value of mass that is going to be created by this. So this will be ILB divided by G. Right, so this is going to be 7.9 amperes of current. Peak value, length is 6.4 power minus 2. Value of B is 0.066, because this is what we found in the previous part. Divide this with 9.81 and you will get an answer of 3.4 into 10 raised to the power minus 3, which means that you're dealing with 3.4 grams. So if positive current is flowing, then there will be an increase of value for the sake of example, right? And if the negative current is flowing because of the AC, then the force will decrease by 3.4, because then the wire will be actually trying to pull the magnet or attract the magnet in the other way. So the mass will decrease by 3.4. So there is a variation of plus minus 3.4. So the total variation comes down to simply 3.4 grams multiplied by 2, which is going to be 6.8 grams of variation. You can check out the marking scheme as well of this question. Okay. All right. Now let's move towards the magnetic field due to current. This is what we've already done in O levels as well. And we try to, I will try to make this as simple as possible. So the direction of current downwards using the right hand grip rule. We point the thumb in the direction of current. So the thumb is pointing downwards. You can hold a pencil if you want to practice this. So the current is moving downwards. So the curl of the fingers is going to go something like this, in this direction. So you can see that the direction of magnetic field around this conductor is actually looking like this. So the circular direction is going to go like this. You can ignore the rest of the signs. It does not matter. You can forget about them. I just wanted to show the direction of magnetic field and how it is found. Now, if, for example, the current are actually in the same direction, the forces on both conductors will be in the opposite direction if they're carrying current in the same direction. Okay. And for example, if the currents are being carried in the opposite direction, then the conductors, this is the opposite, this is the other way around. Basically, when the current is actually opposite, they will be repelling each other. And when the current is same, they will be attracting each other. And the reason for that is the strength of magnetic field. You see, because of this dot model, let's say, the current in this situation is going to go like this. Sorry, the magnetic field is going to go like this. And the magnetic field due to the other current, which is exactly in the same direction with the dot model, is also going to have the same direction. So we see that at the very center, the magnetic field are actually opposite to one another. The first conductor says magnetic field should go up. The second conductor says magnetic field should go down. So the magnetic field at the center becomes weak. On the outer side, we see that if I choose conductor A for my direction of magnetic field, it actually matches with both conductors. So the outer magnetic field becomes stronger, and the magnetic force is from strong region towards a weak region. That's why they're going to attract each other. This is basic O levels or IGCSE. Now, as I discussed earlier, that we are going to discuss the Tesla part as well. So Tesla is a unit of magnetic flux density, and I know that this is a part of a larger formula, F equals to ILB. So what I'm going to do, I'm going to make the subject of the formula be the subject of the formula. And since this is a unit, this is an SI unit, I will define this by putting everything as 1 in the formula. So 1 Newton of force divided by 1 meters of length multiplied by 1 ampere of current. Then the magnetic field strength will be 1 Tesla. So that is how you define units. Okay, so you can phrase this any way you want. You just need to make sure that everything is supposed to be 1. So what can you write down? That if a force of 1 Newton is experienced by a 1 meter length conductor carrying a current of 1 ampere. So you've discussed theoretically all three things. You've talked about force, you've talked about current, you talked about length, and everything is going to be 1. 1 meter, 1 ampere, 1 Newton. Then the magnetic flux density is 1 Tesla. This makes the full definition. Moving on to the current in the wires, as we can see that the direction of the current is upwards, he's going to ask you in the next question to draw the magnetic field lines. So we know that the magnetic field lines in a conductor are actually circular. So they're supposed to be circular. But notice that as I move away from the center, the distance from the center should increase. Now, when you are suggesting this increasing distance between the lines, you are actually telling the examiner that you understand that as you move away from the center of the wire, the strength of magnetic field is going to decrease. So that is very important that you show increasing distance between the lines. Now, since we want to know the direction of magnetic field, let's apply the Fleming's right, not the Fleming's, but the right hand grip rule. The thumb is going to point upwards. You can hold a pencil in front of you pointing upwards like this. If you try to do this with your right hand, the direction of thumb is upwards, leading the pencil, which is actually depicting the direction of current. When you try to hold this pencil in front of you, you will realize that your finger are actually curling this way, like this. So the direction of arrows of the magnet or the magnetic field is actually going to go like this. Okay, all right. The next question is about magnetic flux density of a wire. This is not a part of the syllabus. This formula is not a part of the course. Otherwise, the formula is accurate. Wires' magnetic fields are actually calculated by this method. So he says that calculate the magnetic flux density of wire Y due to the current in wire X. He says that the current of wire X, which is this one, is actually producing a magnetic field, which is very evident on the screen as well. So he says that by the time this magnetic field actually reaches wire Y, how strong is this magnetic field going to be? So this X is actually the distance between the wires. Mu naught is actually the permittivity of free space. You will find this value in the data booklet, and the rest of the values are given to us. So the current is already known, that is 6.3. Let's calculate this value of B. So B is equal to mu naught, which is 4 pi into 10 raised to the power minus 7, multiplied by current, which is just a moment. The current is 6.3. Divide this with the 2 pi given in the formula, and X, which is the distance between them, then that is 4.5 into 10 raised to the power minus 2, because centimeters has to be converted into meters. This B comes out as 28 into 10 raised to the power minus 5 Tesla, but in the marking scheme it's written down as minus 5. So it doesn't matter, you take this one, this is minus 6, you take one decimal over there, it will change from minus 6 to minus 5. Okay, so now he says that the current of 9.3 amperes is now switched on in wire Y, so which means that the current in wire Y now is going to be 9.3 amperes. Now both wires have a current between them, a current in them. He says use your answer in part 2, or in this part that we're trying to we've calculated now, to calculate the force per, now this is where he's going to confuse you. Force per unit length on wire Y. No need to worry about this. You see, the magnetic field is because of wire X on wire Y. So at this point, the magnetic field that actually reaches wire Y is 2.8 into 10 raised to the power minus 5 Tesla. And now it carries a current in its own wire as well. So what will be the force experienced by this wire? So F equals to ILB sine theta. Force experienced, now since it's 4 per unit length, I'm going to take length over there. So this is going to be F divided by L equals to current into magnetic field strength. You see, the current is actually this 9.3 amperes multiplied by the magnetic field caused by the other wire, which is 2.8. So 2.8 power minus 5 gives me the answer of 2.6 minus 4. So 2.6, yeah, 2.6 into 10 raised to the power minus 4 newtons. So 2.6 into 10 raised to the power minus 4 newtons per meter, because now it is force per unit length. Okay, all right. So now he says, this is again a common question, a very good question. He says that the current in the two wires are not equal. We can see that one is 6.4, one is 9.3. Okay, so he says explain whether the force per unit length on the two wires will be the same or different. They are going to be the same. Why? Let's consider two scenarios to understand this. So we have wire X and we have wire Y. Wire X is carrying a current of 6.3 amperes and wire Y is carrying a current of 6.3 and 9.3, yes, 9.3 amperes. And let's consider another scenario with wire X and wire Y, most definitely carrying the same amount of current as 6.3 amperes and as 9.3 amperes. You see, when you want to find out the force per unit length, or at least the force between them, the formula that you're going to use is actually F equals to ILB. Now let's ignore the length part for a bit, because that is going to be the same for both of them, because we're finding the force per unit length. You bring L to the other side and you're left with I and B only. So I'm not going to discuss the length part. I'm only going to discuss the I and B part. So F is equal to IB. Now, what is this magnetic field being caused by? So when you talk about in this scenario, if you're considering the magnetic field due to wire X reaching wire Y, for example, like this, then this magnetic field is due to wire X, then this formula becomes IBX. And since the current is being considered for the second conductor, which is our Y conductor, this formula actually is going to contain the current of Y. So the current of Y experiences a magnetic field due to X. How much force will it experience? Now, when we come to the other side, we realize that the magnetic field is going to be, let's say, if the magnetic field was considered due to Y, because the formula that we're using for B can be used for any wire, right? So the magnetic field, when it reaches the conductor X, is going to look something like this, that now the magnetic field is due to Y and the current is due to the conductor X. So the force is going to come out as IX BY, right? Now notice what's going to happen. You see, when you replace the values of B and current in the respective equation, what you will find? You will find the same answer. How? You see, if I write down F equals to IY BX, what's the formula for B? B has a formula for mu naught I divided by 2 pi x. So IY multiplied by mu naught I of X, because the magnetic field of X is because of the wire X, divided by 2 pi x. Now, this is for this case. If you were dealing with this case, what would it have become? So IX multiplied by mu naught IY divided by 2 pi x. Now notice what has actually happened. You see, IY and IX are still getting multiplied. IX and IY are still getting multiplied. They just swapped places. So even if you were looking at it from this magnetic field perspective or the magnetic field of part B, your answers are going to be the same, because this current gets multiplied by the current of the other wire eventually. So no matter you use this perspective or this perspective, the answer will be the same. So this answer, the answer for this question is that force is proportional to product of Ix and Y. This is what's actually happening. Ix and Iy are getting multiplied no matter which way I look at them. Hence, the force per unit length is same on both conductors, right?